Yes, hi, my dear students. Welcome back to Mission ISRO 2025 by ACE Engineering Academy and ACE Online Platform. In the previous video, I have given you a 20 days preparation strategy, the roadmap to crack Indian Space Research Organization Scientist 2025, right? I hope you guys preparing well and practice more number of numericals, dear students, okay? And today in this video, let us check it out, the previous year questions of electronic devices. And as I already disclosed in the previous video, the weightage for electronic devices is approximately 8 to 10 percentage. And you people know that the syllabus, more than 80% of syllabus in ISRO is similar to GATE examination syllabus. So the students who prepare for GATE examination, ISRO will be very easy for sure. And if you check it out, the numerical standards in ISRO, by now, I hope you got a clarity that, the questions, what they're asking in ISRO is almost like a direct problem solving based questions. So standards of GATE is somewhat higher compared with the ISRO if you check it out, the previous questions. Okay, my dear boys and girls. So anyways, without wasting our time, let us enter into the numericals. I believe you people could be solving with me, and I could expect some answers in the live itself. Okay, dear students, come back. So the very first question, you can check it out onto the screen, my dear boys and girls. So, electron mobility of the following intrinsic elements in descending order. You can check it out, boys and girls. Mobility is always inversely proportional to effective mass. For example, if it is electron mobility, effective mass of electron, inversely proportional to effective mass. I hope you know that. The main formulae for mobility is simply Q times, tau z by m bar. Hope you could recollect from what we have discussed in the class, right? So in the similar way, let me go with some temperature, 300 Kelvin. At 300 Kelvin, if I say for germanium, for silicon, and for gallium arsenide, mobility of electrons and mobility of holes, I have clearly specified in the class. Have you remembered or not, dear students? If I check it out, for germanium, it is almost like a 3800, the units must be centimeter square per volt second. Around 3800 centimeter square per volt second. Similarly, for holes, it is almost like a 1700 centimeter square per volt second. In the similar way, for silicon, mobility of electrons is almost 1350 or around 1300 centimeter square per volt second. And for holes, it is around 500 centimeter square per volt second. And for gallium arsenide, you know that the mobility of electrons are very, very, very high because of very lowest effective mass of the particle. It is almost like a 8600 centimeter square per volt second. And this is around 300 centimeter square per volt second. Therefore, so mobility of electrons of gas, gallium arsenide, is greater than mobility of electrons of germanium, greater than mobility of electrons of silicon. So examiner clearly asking descending order, high level to low level. So highest mobility is for gallium arsenide, moderate is for germanium, and lowest mobility is for silicon. So gallium arsenide, germanium, and silicon. So gallium arsenide, germanium, and silicon. Option A is apt for the given question, right? Option A is correct. Yes, you're right, dear students. You're right. Option A is right. Very good. I'm happy you guys giving the answers. Now, let us enter into the very second question onto the screen. I hope you understood or not, dear students. Option A, because examiner is asking in a descending order. Am I right here? Second question, go through the second question. The common base current gain of a PNP transistor. Students, you know that whenever I say common base, first of all, alpha F, beta F, and gamma F. True or not? What is alpha F? Common base current gain, which is none other than, IC by IE. True or not? In the similar way, what is beta F? Common emitter current gain. So for common emitter, it is IC by IB. In the similar way, what is gamma F? Common collector current gain. For common collector, output is emitter and input is what here? Base, IE by IP. Right, fine. Now, the common base current gain of a PNP bipolar junction transistor is 0.99. So examiner has given this as 0.99. Now the common emitter current gain of the transistor, that means this is how much? If you could remember the formula directly, you can substitute. For example, if a student forgot, no issue. I have given you the logic. We know the universal response, IE, must be always equals to IB plus IC. True or not, dear students, right? IE is always equals to IB plus IC. Now, I need relation between alpha and beta. In alpha and beta, which is common, is IC must be common. So, that current, so-called collector current, as it is common in both, divide that current in this expression. So, if I divide this IE divided by IC, then it will be IB divided by IC plus 1. So, which is current? I mean to say, which is common? Which current is common? Divide with that current in this expression. Then I am very happy to say IE by IC, which is so-called 1 by alpha F, equals to IB by IC, which is 1 by beta F plus 1. That's it. Excuse me, true or not? Therefore, from here, alpha F is simply equals to beta F by 1 plus beta F. Or simply, like alpha F by 1 minus alpha F is equals to beta F. True or not? For example, 1 by alpha F minus 1. 1 minus alpha by alpha equal to 1 by beta. Therefore, alpha by 1 minus alpha is simply equals to beta. So, like that, you can easily, produce the relationships instantly in the exam. There is no need to mug up. My humble request here is, don't mug up. Just try to recollect what exactly the shortcuts, time-saving techniques we have discussed in the class. Okay, my dear boys and girls. Yes, now tell me, it is like 0.99. They're asking beta F right here. Therefore, beta F, which is equals to 0.99 whole divided by, 1 minus alpha F. So, 1 minus 0.99, that is 0.01. I understand this is 99. So, the answer for the given question is 99, which is so-called option C. Anybody? Yes, you're right. Option C, 99 is apt for the given question. Thank you so much. 99 is apt for the given question. Wonderful. So practice more, dear students, and you could at least now understanding the questions are direct problem solving, and more than 80% of the questions are directly formula based questions. Okay, dear students, so you can easily crack Indian Space Research Organization exam, guys. So prepare well for sure, right? And one thing I want to say. We have the limit for this specific video is around 50 minutes to 1 hour, and in 1 hour it is open secret, we can't cover everything. So what could we do in this 1 hour? We are doing, that's it. Okay, now it is your turn to recollect the concepts in a proper way, maintain a good notes, okay, maintain short notes, maintain time-saving techniques, and practice more and more numericals, guys. Okay, now anyways, come back to the third question. Which of the following is true for an NMOS transistor operating in the linear region? I hope students, whenever you go with the region of operations, that is so-called operating regions, okay, because Q-cent point will decide where exactly I biased the MOSFET or a BJT. Once I biased the Q point in a proper operating region, and once I got a confirmation that my Q point is stable, then we are supposed to apply the small signal. Then I am going to use it as an amplifier, or I can use it as a switch, might be like a digital switch, whatnot. Okay, dear students. So, as examiner specified it is NMOS, I need output characteristics, which is so-called VDS versus ID. True or not? So, tell me, dear students, I hope this will be the characteristics what we are going to get. True or not? In the similar way, students, if you check it out here, this is the region which is called over-driven voltage. I mean to say that specific point, that voltage is called over-driven voltage. And this is also called as VDS SAT. True or not? Which is nothing but what here? VGS minus threshold voltage VTH of NMOS. VTH of NMOS. Now speak out, guys. Now this specific region technically called as linear region, whereas this region, technically considered as saturation region, or we say pentode region. This is a triode region, and that is what here? Pentode region. And of course, this region is a breakdown. And this is the characteristics by keeping some VGS is equals to constant at some specific VGS. But take care that VGS must be greater than VTH. Gate to source voltage must be greater than threshold voltage. Then only you could experience a channel in the MOSFET. because it is enhancement MOSFET. Okay, dear students? Right, now speak out. So, whenever you want to operate the Q point in the linear region, then VDS must be lesser than overdriven voltage. That clearly specifies VDS must be lesser than VGS minus VTH. Excuse me, true or not? So, VDS, so NMOS transistor operating in a linear region. So, VDS must be less than VGS minus VTH. VDS must be less than VGS minus VTH. Wonderful. So, option A is apt for the given numerical. Yes, you're right. You're right. Students are giving reply. I'm very happy for that. So, option A is absolutely right, dear students. VDS less than VGS minus VTH. Wonderful, dear students. So, try to practice these type of concepts carefully. Okay, dear students. Now, let me go for one more numerical PYQ. The electrical conductivity. The electrical conductivity of a semiconductor increases when a radiation of wavelength shorter than 1000 nanometers. That is very interesting. Students, if you check it out, for example, if it is EC and if it is EV, hope you know that, valence band and a conduction band. Examiner clearly specified that electrical conductivity is getting increased when you are incidenting a light. That means, you know that whenever I want to increase the current, I need free electrons in the conduction band and holes in the valence band. True or not? So, for that purpose, I think I must give some external energy or a surrounding energy greater than or equal to at least energy gap. Of course, units must be in electron volts. Then only covalent bonds break. We will be getting electron hole pairs. We'll be getting what here? Electron hole pairs, and this is taken as generation rate. So, number of electron hole pairs generated per centimeter cube per second. Now, the question here is, examiner clearly represented that, we are incidenting a light, that is radiation of a wavelength shorter than 1000 nanometers. That means examiner incidenting a light. Whenever light is incident, then it should be, have you remembered or not, energy of a photon. Energy of a photon, it is like a h mu, or we say hf. In the similar way, velocity of a photon or a light is a f lambda. Therefore, if I join both or if I relate both, what could be the energy? It is almost like a, hc by lambda. Now, if energy is in electron volts, okay, in electron volts, then I could represent this as 1.24 by lambda, which is in micrometers, and units must be electron volt. This is the energy of a photon, where lambda wavelength must be in micrometers. No, sir, I need units must be in the order of angstrom units. In that case, so energy which is in electron volt, okay, then it must be 12,400 by lambda, where lambda must be in angstrom units and it must be electron volt. Excuse me, you guys really understanding or not? So, this energy, I repeat, this energy must be greater than or equal to energy gap. It may be, lambda angstrom units or lambda in micrometers. If this energy is greater than or at least equals to energy gap, then you could experience electron hole pair generation. Then in that context, it is GL, generation rate due to light, and these generation of carriers considered as excess carriers, delta N and delta P, because due to light, excess concentration of carriers. And it is open secret, delta N is always equal to delta P because of charge neutrality, right? Yes. Now I'm happy to say, so, from here, examiner has given it is 1000 nanometers, and he is asking what is the band gap. So from here, I can easily measure the band gap. Now speak out, guys. So lambda, which is in micrometers, and he has given as 1000 nanometers. I hope you know. So 1000 nanometers is nothing but 1 micrometer. Excuse me, correct or not? 1000 nanometers is 1 micrometer. You please substitute over here. So 1.24 by 1. Right, 1.24 by 1. Therefore, speak out, guys, 1.24 by 1, which is, I'm going to say 1.24 by 1 electron volts greater than or equal to energy gap electron volt. So, I'm happy to say the energy gap must be at least equals to 1.24 electron volt. So, 1.24, I think this must be right. So, 1.2 electron volt. So, option B is apt for the given question. You're right. Right, this is right. Option B is apt for the given question. I hope you're understanding or not. So not only simply solving the answers, Just I'm trying to recollect at least some concept which is related to that specific topic, by which I believe that will brush up the context. Okay, you can recollect what did you studied exactly. Okay, here don't forget, we are supposed to call it as what here? Excess concentration of carriers. Generation of carriers due to incident light must be always excess concentration of carriers, right? Good. Go with the next numerical. Reason for superior high frequency performance of a metal semiconductor diode compared to the PN junction diode. Wonderful. Students, you know that whenever we go with the metal to semiconductor, I repeat, metal to semiconductor, that is a Schottky diode. And default, we should always consider metal, metal to N type. I repeat, metal to N type. Schottky barrier diode. Okay, so metal to N type. I discussed a lot. What happens when there exists junction between metal and semiconductor? I discussed. After discussing that specific topic only, we went for a MOS, metal oxide semiconductor. Hope you remember the classes, right, dear students? Anyways, so metal to N type. And in very rare case, for some specific applications, very rare case, some industries are using metal with a P-type semiconductor. There is not N type for some specific task. It is like a special purpose application, not for a general purpose. Okay, metal to P-type also they are using. But in the exam prospective, it might be gate exam or engineering services or going for ISRO or PSUs, anything. If no condition is specified in the exam, if no condition is specified by the examiner, default metal to semiconductor diode is always metal to N type. Don't take P type until and unless it is specified by the examiner. So default, we are supposed to choose metal to N type semiconductor. I hope you got the point, dear students. Therefore, this is metal, that is N type. That means current is due to only majority concentration of carriers. Therefore, there is no minority effects. The effects what you experience in a PN junction diode, those effects you can't experience in this situation. Moreover, in a Schottky diode, the advantage is the capacitance impact is not there. The diffusion capacitance is almost zero and the transition capacitance is negligible. Due to that, the transition frequency is very high. Upper cutoff frequency is very high. And the switching speed is very high and time delay is negligible. That's a beauty of using a Schottky diode, fastest switching response. Now come back with the options what examiner has specified. So again, reason for superior high frequency performance of metal to semiconductor diode compared to the PN diode. Simple answer. Without seeing options, we can say there is no capacitance effect. That too, the minority charge storage concept is not there. Okay, have a look carefully. Higher conductivity of metal compared to the semiconductor? No. That is not responsible for, switching speed. And no minority carrier storage impact or effect in metal semiconductor. Perfect. There is no minority charge storage. As I already told you, for example, let me go for switching of a diode or a transient behavior of a PN junction diode. So due to the capacitance behavior, if a diode is switching from forward bias to reverse bias, immediately it can't be shifted to the reverse bias. That means due to the capacitance nature, it never accepts sudden changes in the voltage. It takes some time. That is so-called reverse recovery time. In reverse recovery time, what we have? One is a transit time, that is so-called transition time, and other is charge storage removable time. One is what here? In the reverse recovery time, what is included? One is a transition time, other is a charge storage removable time. Guys, okay, that is what we have seen in case of PN junction diode. But here, in case of Schottky diode, there is no concept of charge storage. Of course, transition time is there from forward bias to reverse bias to forward bias. Switching transition time is there, but there is no charge storage removable time. Therefore, the reverse recovery time is depending on only the transition time. There is no, charge storage removable time. So this is one of the main reasons why for fastest switching response, most of the industries prefer Schottky barrier diode compared with the PN junction diode. So this absolutely giving a high priority for the options. Check out the option 3. Metal semiconductor junction doesn't rectify. No, it is rectifying and it is radio frequency. Absolutely, it can be used as a rectifier. High frequency signals, right? And hole is the majority carrier. I'm sorry, I told number of times, if no condition is given, default metal to semiconductor is metal to n-type. In that case, electrons are only majority carriers, not holes. So the only choice here is option B. Yes, option B is apt for the given question. I hope you guys really understanding or not, dear students, right? Try to recollect the concepts what I have discussed clearly in the classes. Okay, right. Anyways, come back to one more question. Yeah, this is for your notes. Okay, so in Schottky diode, reverse recovery time includes only, yes, that's what I said, transition time. There is no charge storage removable time. Right, dear students? So take it as a note, which is very important because instead of writing, I have given already. By that I can save time at least. If I write everything on the board right now, where the limit of time is just 55 minutes to 1 hour, I don't think so. That will take that. I don't think so. That is advisable. So that's the reason why I have written already here, right? Anyways, come back, dear students. Have a look carefully. Which statement? Oh, again a Schottky barrier diode. Wonderful. So which statement is correct for Schottky diode, right? Anyways, CV, that is I meant to say VI, current voltage characteristics is totally different than that of a PN junction diode. Okay, and no, the VI graph is almost similar. It may be a Schottky diode or it may be a PN diode. The VI graph is almost similar. So this is wrong. The current is controlled by the diffusion of minority. I don't think so, because I told already, minority impact is negligible in case of Schottky, right? Because default is a metal to n-type. It is electron, even that is also electron, right? So this is wrong. And the current results from flow of minority carriers. No, I told already, it's a majority carrier device. If no condition is given, default Schottky diode is always a majority carrier device. And the storage time is almost zero. You're right. The charge storage time is negligible because of the capacitance impact. Capacitance is almost negligible, right? So the charge storage removable time is almost negligible. So this is apt for the given question. So option D, yes, you're right. Option D is apt for the given question. Schottky barrier diode. Of course, in 2016 we have, right? Anyways, come back. Photodiodes operate. Students, I hope you remember, right? We have optoelectronic devices, like we have photodiodes, we have light emitting diodes, we have solar cell, right, and laser diodes, whatnot. For example, if I consider the diode equation, I is nothing but I naught, exponential diode voltage by eta Vt minus 1. This is the diode current. True or not? And this current is mixed with the photo current. So no doubt it is mixed with the photo current. Let me say minus IL. IL is nothing but what is current due to light. I repeat, current due to light. Now my question here is, students, listen my words carefully. My question here is, for example, I operate my diode in the forward bias. Assume that I operate my diode in the forward bias. Then in that case, diode voltage will be positive. Now speak out, if diode voltage is positive, I think this exponential term is very high. True or not? This exponential quantity is very high. So this value is a highest value compared to the photo current. In that case, the total current is almost equal to this current. Then how can I get a photo current there? Because photo current is getting neglected compared to the current I am getting because of the applied voltage. That means in the forward bias, even though I am giving light, the current due to light is negligible compared with the current I am getting due to the applied voltage. Then I don't think so. I am going to get the photo current. Photodiode main task is to get a photo current. So diode in the forward bias has no meaning to produce a photo current. Now let me interchange, instead of plus, let me keep it as a minus. That means what? Cathode voltage greater than anode voltage. If diode is forward bias, anode voltage is greater than cathode voltage. Whereas if diode is reverse bias, cathode voltage is greater than anode voltage. In that case, now this is negative. Now speak out. I think this value is negligible compared to the other quantities because exponential negative is very, very, very small. In that case, the total diode current is almost equals to minus I naught minus IL. And of course, this leakage current is in the order of microamps for germanium, nanoamps for silicon and picoamps for gallium arsenide. And this photocurrent strictly depends on generation rate due to light. And that is a very good quantity compared to this one. Therefore, ideally, diode current is almost equal to photocurrent. So if you are interested to produce photocurrents, you are supposed to neglect this expression. Indicates a diode voltage must be negative. Indicates cathode voltage must be greater than anode voltage. Indicates a diode must be always reverse biased. So very simple logic. Therefore, photodiodes must be always reverse biased. So photodiodes must be always operates under reverse bias. That's it. This is the way how you need to recollect the concepts what we have discussed. That, dear students, very easy concept, right? Now, anyways, come back to one more very interesting question. In a photodiode, with the increase in the reverse bias, in a photodiode with the increase in the reverse bias, the reverse saturation current in a PN junction, in a PN junction diode with increase in the reverse bias. Students, for example, I say diode current ID is equals to I naught exponential diode voltage by Vt or eta Vt, okay, minus 1. So whenever I say in case of a reverse bias, in reverse bias diode voltage is negative, then I understand initially it will be exponential decay. Right here, for example, if I take a graph, it is minus Vd and it is minus Id. So initially it is exponential decay. Now whenever this voltage is getting increased, if the voltage is getting increased, I think this value is becoming negligible compared to minus 1 or 1, the magnitude 1. Then in that context, then diode current is almost equals to I naught, of course, minus I naught. And I'm happy to say this I naught depends on what here? Ni square. And I hope Ni square depends on T cube. I hope you remembered. Ni square is equals to A naught T cube exponential minus Eg naught by Kt. That means what? It is strictly depends on temperature and energy gap of the material. That means the leakage current strictly depends on what here? Temperature and energy gap of the material, and of course depends on the doping. So the leakage currents depends on the temperature, leakage currents depends on the doping, leakage currents depends on the type of material. That is called energy gap of the material, because for germanium, silicon, gas, different materials, different energy gap, so different leakage currents. That means the leakage current is not depends on the voltage. Therefore, it is straight line. If it is an ideal diode, it is a straight line, and this is minus I naught. Okay, so now have a look carefully. In a PN diode, no condition is given. Okay, in a PN diode, with the increase in the reverse bias, the reverse current simply, I could say, remains constant. Whereas if it is a practical diode, the graph will be in this way. The graph will be in this way. But commonly in public sector undertakings, if no condition is specified, we eliminated traps, because this is the graph. I hope you remembered. This is the graph where we are getting due to traps. SRH recombination, Shockley-Reed-Hall, SRH recombination. I hope you remembered. Recombination rate U is equals to 1 by tau into N dot P minus Ni square by N plus P plus. It is almost like a 2 Ni like that. It is almost the formula is like this. So this is nothing but the recombination rate. Or a generation rate. So that based on SRH, Shockley-Reed-Hall. Based on that, by solving in the reverse bias, the generation rate is getting dominated due to traps in the depletion region, because of we are getting the graph in this way. But in the PSUs, public sector undertakings, if no condition is specified, commonly we neglect the SRH recombination rate and all the things. In that case, this slope need not to be considered. Then we need to consider only the straight line. In that case, the answer for the given question is option C, remains constant. Right, my dear boys and girls, I hope you're able to understand the way how to decode the given questions. Right, anyways, come back to one more interesting question. Have a look carefully, guys. Right, now, it is 2016 again. If alpha, right, alpha F, if it is given as 0.98 and I say naught 6 microampere, and this is IB, I think, IB, okay, base current, IB, it is almost like 100 microamps. Now then the value for IC, it is very easy question. IB is given, I hope you know relation between IC and IB. IC is equals to beta F times IB, that is fine. But examiner has given leakage current, then you are supposed to include leakage current. You know the formula, dears, IC is equals to alpha F times IE with leakage is ICBO. The same expression, if I use it as beta F times IB, then it should be ICEO. And we know that ICBO is almost equals to IC naught, which is simply equals to, as per the given question, 6 microamps. 6 microamps. In the similar way, what is the ICEO, dear students? ICEO is nothing but 1 plus beta F times ICBO. Excuse me, right? 1 plus beta F times ICBO. Therefore, if I could do that, beta F times IB plus, 1 plus beta F times IC naught. That's it. I think IC naught is given by the examiner, and IB is given by the examiner, and alpha F is given by the examiner. If I know beta, I'm going to get the answer. I hope you know beta. What is relation between beta F and alpha F? Beta F is equals to alpha F by 1 minus alpha F, and 1 plus beta F is nothing but 1 by 1 minus alpha F. That's it. Now substitute the given data, alpha F like 0.98 by 1 minus 0.98, and 1 plus beta F as 1 by 1 minus alpha F. I hope here you're going to get as a 49. This will be 49, and this will be 50, right? You please substitute there, you're going to get the value for IC. So you please put pen on the paper here. After solving the answer, what I have, I'm giving you here. By that, you please put pen on the paper. I can save time because these calculations, you guys can do that. By that, I can do more numericals instead of spending more time for the calculations, right? I understand we got, it is almost like a 5.2 milliampere. Put pen on the paper. I appeal everybody in the class, at least after completion of my video, okay, put pen on the paper, right? So 5.2 milliamps, 5.2 milliamps, option D is apt for the given numerical, 5.2 milliamps. Got the point, dear students? I hope you remembered this, you understood this. Right, dear students? Anyways, come back with one more very interesting question. Have a look carefully, guys. So, if a donor type impurity is added to the semiconductor, then at a given temperature, the Fermi level. Very interesting. You know that whenever temperature increases at a constant doping, for example, let me tell you, the universal formulae N naught, concentration of electrons in the conduction band N naught. Okay, N naught is nothing but what here? NC exponential, EF minus EC by KT. True or not, everybody in the class? Therefore, could you please let me know what is EF minus EC? EF minus EC is equals to KT log mod N naught by NC base E. Or we say EC minus EF is nothing but what here? KT log mod NC by N naught base E. And of course, you know that where N naught is nothing but what, dear students? ND by 2 plus root of ND by 2 whole square plus Ni square. And if no condition is specified, commonly we operate at the temperatures under 250 degree Kelvin to 350 or 400 degree Kelvin. Commonly in that range only, it is advisable to operate our electronic devices. Ideally, 300 Kelvin is most advisable, so-called thermal equilibrium systems. So in that case, then N naught is almost equals to ND. More precisely, it should be ND plus. I hope you know that. ND plus, ionized donor impurity. And again, if no condition is specified, we go for 100% ionization, then ND plus is equals to ND. In that case, N naught, which is so-called ND plus, and for 100% ionization, it is equals to ND. Now, if I could substitute that, what I'm going to get here, EC minus EF is equals to KT log mod NC by ND base E. I hope you got it. Now, very simple logic. If ND is increasing, that means a donor doping is increasing, then EC minus EF will be decreasing. EC minus EF, the difference. So, this is EC, right, dear students, and this is EF. and here somewhere we have EV. So whenever EC minus EF is getting decreased, I think Fermi level is moving towards conduction band. Very simple answer, right? Now tell me, dear students, if a donor type impurity is added to the semiconductor, then at a specific temperature, the Fermi level move towards the center. No. Move towards the center indicates EC minus EF must be increasing. That means that will happen when temperature increases. So this is wrong. Move towards the valence band. No, that is p-type semiconductor. Move towards conduction band. Absolutely right. Correct or not? It is the Fermi level, because the difference between EC and EF is getting decreased. So Fermi level is moving towards the conduction band is right. So doesn't change is absolutely wrong. So option C is apt for the given question. Hope you understood, right, dear students? Come back. Next question. Yeah, have a look carefully, dear students. Next question. A small amount of phosphorus is added to silicon. Students, the given semiconductor is silicon, and phosphorus is added. That clearly represents it is N-type semiconductor. Arsenic, antimony, phosphorus, bismuth, right? It is N-type semiconductor. Now, so that there are 2.5 into 10 power 17 conduction electrons per meter cube. So, let me say N naught, or we say N and naught, better. Let me write N and naught. Yeah, how much examiner has given? 2.5 into 10 power 17 per meter cube, right? And 9.0 into 10 power 14, I think Pn naught, because N-type semiconductor, holes represents what here? Minority concentration of carriers. So Pn naught, how much? 9 into 10 power 14 per meter cube. Now let mobility of electrons, examiner has given 0.13 meter square per volt second, and the mobility of holes, 0.05 meter square per volt second. See, this is what in the first question I have given. Mobility of electrons for silicon at a 300 Kelvin, 1350 or 1300 centimeter square per volt second. Now it is meter square. Mobility of holes, what I told you, 500 centimeter square per volt second, and it is given as 0.05 meter square per volt second. The same value, right? Now, examiner is asking to find resistivity. Students, it is very easy. Resistivity, that rho is nothing but 1 by sigma. Excuse me, correct or not? And examiner clearly specified, this is a semiconductor. Whenever I go with the semiconductor, I hope you know that 1 by NQ mu N plus PQ mu P. That's it. Excuse me, correct or not? 1 by NQ mu N plus PQ mu P. And examiner, what he has given? N he has given, P he has given, Q we know that, mobility of electrons he has given, mobility of holes he has given. So first find the conductivity and reciprocate that, you are going to get the value for rho, and everything is in meters. Even options, examiner is asking in terms of meters, so no need to change units. My humble appeal, everybody in the class, concentrate on units also, please. Okay, so no need to change any units. I can easily get the answer. Put pen on the paper, you're going to get the answer, and the answer is around 192. What I got here is 192.04 ohm meters. So 192 indicates option B is apt for the given question. Very easy questions, right? That's what I said, numerical based questions. Direct formulae under numerical based questions you could expect in ISRO exam. Okay, dear students, the students who prepared for GATE exam, they can easily solve the questions in Indian Space Research Organization. Right, dear students? Okay, anyways, come back with one more question. Have a look carefully. Silicon dioxide is used in integrated circuits. Yes, I can easily get this answer directly, dear students. As I told you while discussing about a p-n junction diode, what is the need of using a silicon dioxide? I have clearly exposed. And while discussing about a MOSFET, I discussed what is the need of using silicon dioxide. Check out the options, because it facilitates the penetration of diffusions. No, it is not exactly. And because of its high heat conduction, no, it will control the diffusion of carriers. It will control the doping diffusion percentage, right? So to control the location of diffusion and to protect and insulate the silicon surface, perfect. This is apt for the given question. And to control the concentration of diffusions, no, it is wrong. So option C is apt for the given question. Very easy question. Go with one more interesting question. the wavelength of emitted radiation by electron, while transiting from one energy state to another energy state. Okay, wavelength of emitted radiation, that clearly represents it is a direct bandgap semiconductor. Direct bandgap semiconductor. I think I discussed it clearly about the EK diagram, y-axis energy, x-axis is the momentum vector, EK diagram. So in that case, direct bandgap semiconductor, for example, if it is EC and if it is EV, I'm taking example as direct bandgap. Is it okay here because of emitted radiation, and the carriers must diffuse from high level to low level. Due to the direct bandgap, it releases energy. That energy must be in terms of light, and of course this can be represented as 1.24 by lambda micrometers electron volt, or I can represent this as 12,400 by lambda angstrom units electron volt. That's it. Now what is exactly examiner is asking? So it is transiting from one state to other state. This is high level to low level, because whenever it want to emit, it should jump from high level to low level. High level must be always -5 electron volt, and low level is -15 electron volt. That means this value must be -5 electron volt and this value must be -15 electron volt. Therefore, I'm happy to say, delta E, the difference in the energy is nothing but what here? EC minus EV, because it is energy gap. This value, how much here? It is greater than or equal to, at least equal to energy gap. What is energy gap? EC minus EV. Energy gap is what? EC minus EV. That means difference in the energy level. Energy gap is what? EC minus EV, difference in the energy level. That difference I'm putting it as delta E here. Now, how much it is, students? Because examiner is expecting answer in terms of angstrom units. So let me put angstrom units. So then 12,400 by lambda must be in angstrom units, and this must be electron volt. Then delta E, -5 -15, that means 10. This is a 10 electron volt is equal to 12,400 by lambda angstrom units. Units must be electron volt here. Very easy, right? Therefore, lambda in angstrom units must be equals to 1240 angstrom units. Very easy question. So answer for the given question is 1240. So option B is apt. 1240. Right. Option B. Option B is apt for the given question. Okay. I hope, my dear students, you are enjoying these questions right here. Okay. Anyways, come back to one more very interesting question. Have a look carefully, guys. How does the dynamic resistance of diode varies with the temperature? Students, you know that the dynamic resistance, for example, I say RAC, or we say small signal resistance, is nothing but how much, dear students? VT by IDQ. I hope you remember thermal voltage by IDQ, the formula. And it is with respect to temperature. I think it is a KT by Q whole divided by IDQ. Therefore, RAC proportional to temperature. He is asking about a dynamic resistance varies with temperature. So temperature increases, dynamic resistance increases, directly proportional. Directly proportional is apt. Inversely is wrong. Independent is wrong. Directly to the square, no, it is wrong. It is directly proportional to only temperature. So answer for the given question is option A. Okay. Now one more question. Right. Two initially identical samples A and B of a pure germanium are doped with the donor concentrations. So there are two materials, material A and material B, and both are N-type semiconductors. So this is again, this is N-type, and even this is what here, N-type, right? And donor concentrations. So I could say ND in A is how much, guys? 1 into 10 power 20, 1 into 10 power 20, and NDB, how much, dear students? 3 into 10 power 20, 3 into 10 power 20 respectively. If the whole concentration in A, then in that case, let me take NA is approximately, because original formula is how much? NN naught is nothing but what here? ND by 2 plus root of ND by 2 whole square plus NI square. As I told you, if I operate at the regular operating temperatures around the 300 Kelvin, Ni value is negligible compared to the doping. So it is approximately equal to Nd. More precisely, it should be Nd plus, but no condition is given. 100% ionization I can take. So Nn naught is almost equal to Nd. Every time while doing numerical, try to recollect it. Then you don't do mistake. Even minute things are very important in case of the competitive exams like ISRO, DRDO, whatnot. Okay, dear students. Right. So in the similar way, even here I can take NNB approximately. Right, boys and girls. Now, examiner has given the whole concentration in A. That means what? PNA. How much, dears? It is like 9 into 10 power 12 units. I hope now he is asking, at the same temperature, what is PNB? Very easy question. Students, if no condition is specified, we are supposed to go under equilibrium condition. In that case, we know mass action law, N dot P equal to Ni square. Therefore, can I use a statement like this, right? NNA, PNA is equals to NNB, PNB, because it is equal to Ni square, and examiner clearly told it is a constant temperature and the two devices are identical. So I hope I can use this formula. I think NNA he has given 1 into 10 power 20, PNA he has given 9 into 10 power 12 by, speak out guys, NNB he has given 3 into 10 power 20. Now what will be PNB? Therefore from here, what is PNB, dear students? So 10 power 20, 10 power 20 nullified, 3 3s are 9. So 3 into 10 power 12, 3 into 10 power 12. So 3 into 10 power 12. Option A is apt for the given question. Option A, right? Okay, units are in meter cube. Okay, fine. Here he has not specified any units, but as per the options, it is under meter cube, fine. Because I have not taken either centimeters or meters like that. I have taken just as units. So answer for the given question is option A. Right, my dear students? Go with one more interesting question. Right, the built-in potential or a diffusion potential in a PN junction. The built-in potential, hope you have remembered the built-in potential. This is the formula. Built-in potential is equals to KT by Q, log ND NA by Ni square basic. And this can be done, this can be calculated at equilibrium. Am I right here? Whenever I say equilibrium, then Fermi level EFN is always equal to EFP. Correct or not? Because the Fermi level will be not having any slope. No slope in the Fermi level. It's because it is at equilibrium, it must be straight line. Now have a look carefully. Now the built-in potential or a diffusion potential in a PN junction is equal to the difference of Fermi levels. Absolutely wrong. What is the difference of Fermi levels? It is nothing but diode voltage or applied voltage. So the difference of Fermi levels, for example, Fn minus Fp, quasi-Fermi levels. You know that if equilibrium is disturbed, then that is called quasi-equilibrium. Then that Fermi level is called quasi-Fermi level. So Fn minus Fp is nothing but Q times the diode voltage or applied voltage. It is not a built-in voltage. It is a diode voltage. So option A is wrong. Next. So increases with increase in doping levels. Interesting. Yes, it is right. Whenever doping is increasing, for built-in voltage increases, right? If doping increases, come on, you can check it out here. If doping increases, built-in voltage increases. Perfect. So option B is correct. What about option C? Increases with increase in temperature. No. Some students are misunderstanding that. Sir, temperature is here. If temperature increases, built-in voltage increases. Some students are misunderstanding that. Sir, you can see here, if temperature increases, built-in voltage increases. No, I clearly specified in the class. What is that? Not only here I have temperature, this is the place where the temperature exists. This is also the place. What is that? Ni square. Ni square is equals to A naught T cube exponential minus, Eg naught by KT. So, Ni square, it is depending on T power 3. So if temperature is increasing compared to the percentage of this, the percentage here increasing is more. Therefore, if temperature increases, built-in voltage decreases. So tell me, yes, if temperature increases, no doubt, built-in voltage decreases. But he told that increases with increase in temperature, which is absolutely wrong. So, and all the above is absolutely wrong. The only choice for the given question is option B. Option B is apt for the given question. I hope you're really understanding or not the way how we have the questions and the things. Right, my dear boys and girls? Anyways, go with one more question. So the dominant mechanism for motion of charge carriers in the forward and reverse bias silicon p-n junctions. You know that in the forward bias, what is the dominant mechanism for producing currents? Diffusion. Because excess carriers if the majority carriers cross junction, they become excess minority carrier. So and moreover, we always follow low level injection. In the forward bias, we always follow low level injection. So forward bias, dominant mechanism is diffusion, and in the reverse bias, because of the junction electric field, built-in electric field, there exists a huge current which is so called as a drift mechanism. So in the forward bias, diffusion is dominating. In the reverse bias, drift is dominating. Now speak out, guys. Diffusion in the forward bias, drift in the reverse bias is apt for the given question. It is apt for the given question, right? So like that, lot of questions we have. Do one thing, dear students. Let me because of the time which is of very limited. Let me do this question. Okay, let me do this question. Yeah, very limited time we have, so let me do this question. Very interesting question. Have a look carefully, dears. In the given circuit, the switch S1, here S1 is given, remains closed, and S2 remains open for the long time. Okay, fine. So like S1 is closed and S2 is open for a long time. Whereas at t is equal to 0, S1 opens. At t equal to 0, the switch S1 is open. Whereas at t equal to 0, S2 is closed. Okay, fine. And remains this position for a long time. It's a transient. Wonderful. Now find the drain current for t less than 0 and t greater than 0. Wonderful, dear students. Let me check it out carefully here. See, for t less than 0. Now check out the circuit. This is the circuit. For t less than 0, I think this switch is closed and this switch is open. That means what? S1 is closed and S2 is what here? Open. So if I go with that MOSFET, I think this is closed. Excuse me, right, dear student? This is closed, right? And what is this voltage? Here it is a 3 volt and that is a 2 volt. Okay, now speak out. It is a 3 volt, it is a 2 volt, and the threshold voltage is given as a 0.5 volt. It is NMOS. Now, okay, fine, sorry, fine. Now find the drain current he is asking. Okay, let's move that. Drain current. First of all, if I want to find the drain current, the first thing is whether my MOSFET is on or not. That I need to check. Now check it out, guys. VGS. Find VGS. I think what is VGS here? VG minus VS. That means 3 minus 0, which is a 3 volt. I am happy that VGS greater than threshold voltage. Therefore, MOSFET is on. Yes, there is a conduction. Now, whenever MOSFET is on, then what we should understand, whether it is a linear or a saturation. If it is a linear, that means Q point. If it is a linear, we should use a linear formulae. If it is a saturation, we should use a saturation formulae. And the examiner has not provided any condition, then there is no need to consider any early effect. No channel length modulation, no need to consider anything. No early effect. Okay. Anyways, have a look carefully and don't forget, early effect, you are supposed to choose in the saturation mode, not in the linear mode, right? Now tell me whether it is a linear or saturation. In that case, please let me know, dear students, what is VGS? Okay, just a minute. What is VDS and VGS minus VTH? This relation I need. If VDS greater than VGS minus VTH, Q point is under saturation. If VDS less than VGS minus VTH, Q point is under linear. Correct or not? Because VGS minus VTH is over-driven voltage, or VDS is at. Now let me know what is VDS. So 2 minus 0, it is a 2 volt. What is VGS? 3 minus 0, this is 3 volt minus 0.5 volt. So I understand it is lesser than. My God, therefore Q point is in linear. Wonderful. So now tell me, whenever Q point is under linear, what could be the formula? ID is equals to mu n cox dash W by L into VGS minus VTH into VDS minus half VDS square. This is the formula. Mu n Cox dash, yes, examiner has given, it's a Cox dash, okay, because amperes per volt square, okay, oxide capacitance per unit area. It is not oxide capacitance, it is oxide capacitance per unit area, right? So examiner has provided 100 microamps per volt square, and aspect ratio, that is W by L, that is 2. If I could substitute everything, I believe what answer I got, it is almost like a 600 microampere. So the very first question, that is for t less than 0. For t less than 0, the answer for the given question is what here? 600 microampere. In the similar way, for t greater than 0, I think this case, t greater than 0. T greater than 0 indicates what? At t equal to 0 itself, this switch is open, that switch is closed. Excuse me, correct or not? Then in that case, for t greater than 0, then the device will be in this way. Here it is a 4 volt, and here he provided as a 2 volt, 3 volt, and of course threshold voltage is 0.5 volt. Now tell me, dear students, first what I should consider, whether MOSFET is on or off. If it is on, Q point is under linear or saturation. Now have a look carefully. What is VGS? So VGS is simply 3 minus 4. My God, it is minus 1 volt. I think VGS is less than threshold voltage. Oh my God. So Q point is in cutoff. Superb. Q point is in cutoff. Whenever Q point is in cutoff, there is no current. Therefore, IDQ is simply 0. Wonderful. So the first answer is a 600 microamps and second answer is 0. So 600 microamps and 0. I think option A is apt for the given question. Option B, 625, wrong. Option C, 600 minus 25, wrong. And option D, 0 and 600, no, wrong. So option A is apt for the given question. Guys, I hope understanding or not, everybody in the class, hope you're really enjoying solving this type of beautiful numericals, right? In a similar way, let me go with one more interesting question. Have a look carefully. Check it out, dear student, just a minute. Yeah, I hope it is visible, right? Yeah, check it out this question, dears. The output characteristics of a BJT amplifier is given. See, output graph of a bipolar junction transistor is given. Find the minimum collector current required for R0. Excuse me, it is very clear by the characteristics, this voltage is technically called as early voltage. Am I right here? This is called early voltage. Of course, take a magnitude, not minus 50, take it as a magnitude. And because of that early voltage, there is a resistance, so-called output resistance R0. So R0, I hope you know, early voltage by the collector current, Q point, ICQ. I hope now we are supposed to find ICQ, which is so-called early voltage by R0. Early voltage, examiner has given as 50 volt by R0. R0, examiner has clearly specified as 50 K. I think it is a 1 milliampere. Therefore, the current, what we are getting here is 1 milliamps. I think option A is apt for the given question. Excuse me, understanding or not? So like that, my dear boys and girls, you can do many more numericals. Might be BJT, might be MOSFET, might be generation and recombination of charge carriers, might be diodes, might be, a breakdown mechanism, whatnot. By now, you got some clarity the way how they are asking questions in Indian Space Research Organization. Of course, these are all 2020 questions. ISRO 2020, the latest, because 2021, 2022, they have not conducted any exams, I understand. So, dear students, I understand, you students surely will reach your target because your preparation will not be wasted for sure. So, make sure, repeat the concepts until you understand. Try to get command in the subject, maintain a very proper short notes. Try to repeat the same concepts even though but try to repeat it number of times until you got command in the subject. That is what only thing I could say. And best wishes for your wonderful career and have a healthy and wealthy future. Reach your target with a great confidence, my dear students. And thank you so much.